We found ourselves in the tunnels of another hollowed-out asteroid, but this one was a bit larger and with a larger crew than the geoengineering station. This time the apparent leader had 4 legs and a chitinous exoskeleton reminiscent in some ways of the civilians, but lacking their ability to change color. It was a bright yellow over all of its body except for the pitch-black eyes and the dark green mark of the Curators on its back. Another asteroid. Emma asked after we made introductions. How many of these things do you have? You should properly ask how many we have since you have joined us. The answer is 6. This station is responsible for all maintenance between the introduction of life and the curation of multicellular life forms. We deliberately trigger several important events if they do not occur naturally, and we also intervene sometimes when things take a bad turn. Simple ecosystems are inherently perilous, responding poorly to external insults or feedback overshoot. How long do you stay at each world? Our mission is very different from that of the engineers you recently met. Congratulations on witnessing the final engineered collision, by the way. Once they identify a promising system, they stick with it for tens of thousands of years. Because once you start banging stuff around in a forming inner solar system, it's not unusual to need adjustments often. They will have thousands of systems on survey rotation when they're not engineering, mostly in easily identified stellar nurseries, and when they pick a candidate system for curation, it becomes their focus for some time. Our mission is a bit different. Once the engineers turn a new world over to us, we add it to our private index. We are curating 9.3 million worlds at this time, but few of them are visited more than once every few million years. The closer a world gets to hosting a critical path species, the more often it requires attention. At the stages where we are involved, everything involves very long time scales, so we are able to attend many worlds. It would be unusual for us to prolong a visit to any individual world for more than a few weeks. Since we have many to choose from, we've put together a little tour that should give you an idea how our attention progresses as a world develops in these early eons. We were assigned quarters and told that our tour would last a couple of months. The crew was again a wild mix of species, and this time several times more numerous than the crew of the engineering station. Dealing with living things, even simple ones, requires us to maintain laboratories and skill sets of considerable complexity, the leader said. Arranging your tour was easy because our usual pattern is to try to mix things up, so that everyone has a job to do with some regularity. Food was served in a common hall but customized for the many individual species who were present. A similar arrangement prevails in capital fold ships. The quality and attention to preparation detail were superb. Most of us will live a very long lifetime aboard this station, the leader said when we mentioned this. Our quality of life is an important consideration. When were the asteroid stations built? I asked. We don't know for certain. They are at least 5 billion years old, but we have no reliable records from those early eons. We have studied the matter and concluded that all the host asteroids were formed in the same solar nebula about 9 billion years ago. It would seem sensible to conclude that that was the home system of the ancestors, but we have no proof of that. The ancestors are the original curators who evolved naturally. Exactly. I forget that you are so new to all of this. I wonder why they used asteroids, Emma said. Nobody uses asteroids. Our theory is that the ancestors developed advanced fold technology before they developed nanites. If you ask your implants, I'm sending you a link, you will find you have the skill of fold nibble excavation. This makes it very easy to turn a solid ball of rock or metal into a warren of tunnels and rooms. Sure enough, Emma and I both found ourselves remembering how to execute this technique, which used precisely formed fold apertures to remove slabs of rock 10 to 15 centimeters thick from the end of a tunnel in progress. This technique was not accessible to the curated species, because they did not have the precision fold technology enjoyed by the curators. But it suggested that familiar modern nanite tech, capable of cheaply building large ships, was developed by the ancestors sometime later than their advanced fold tech. Our first stop was a world that had experienced its own final engineered collision only about 50 million years previously. The solar system was still in the throes of what our scientists would call the late heavy bombardment, and both the world and its moon were pocked with lava-filled craters from recent impacts. There is really nothing for us to do here, our host explained, but we check in to see how it's progressing. We will use what we learn here to schedule our next visit. Sometimes if things are going badly, we might also refer such a world back to the engineers. Sometimes we just learn that it isn't going to work out and cancel it from our index. None of this is an exact science even for us. After a few hours, the head of the planetary astronomy crew made her report. Outer planet orbit inflation is a bit ahead of what the engineers expected, but not really a problem. Density of impacting debris is decreasing on schedule. The moon's orbit is looking good. Water cover is behind schedule, but there is plenty of material left for delivery in the bombardment. Overall, we think 30 million years is a good return date. We should be able to get a better idea what the final ocean volume will be by then. The mission leader entered that into a log and said, "Scheduled then." That's it? There isn't much else we can do at this stage. This world is still receiving extinction-level impact several times a year, and it needs those impactors to deliver water and organic material which was driven off during the even more violent early days. We mainly came to make sure there were no unfortunate mishaps developing. Sometimes we find there won't be enough water, or that the relationship between the moon's orbit and the planet's rotation is unpromising. Sometimes the outer system gives us an unfortunate surprise. About 10% of the worlds the engineers bring to this point turn out to be unsuitable, and we either get the engineers to try to fix them, or if that's not possible, we give up and move on. While the station had far better fold drives than even those humans had built, we were folding into systems that hadn't been visited for millions of years, so we moved in cautiously, taking several survey days in the relative safety of the outer system before folding in toward the candidate world. Our next target was further along, and while it was barren, it glistened in places with full ocean basins and had no large open pits of lava. The moon already strongly resembled Earth's Luna. This world received its moon 300 million years ago, the leader told us. Its atmosphere is mostly water, sulfur dioxide, and carbon dioxide. Tidal forces have slowed its rotation and pulled the moon upward to an orbit which makes the tides much less violent. Our notes show that we had hoped life would have emerged naturally by now. It does about 20% of the time. The atmospheric analysis makes it pretty certain that this hasn't happened, so you will get to see a seeding operation here. Since the atmosphere was still quite toxic even to Curators, the life science crew conducted their survey in single-being personal flyers. These were small enough that a Curator's implant could fold them a reasonable distance, or generate a supergravity propulsion field sufficient for maneuvering. The scientists spent several days surveying the world and several more deciding on a fertilization strategy. Then cryogenic storage containers in the heart of the station were opened and carefully selected microorganisms stored within were cultured to generate enough seed pods to give the operation a good chance of success. Finally, thousands of these pods were delivered to carefully selected surface sites, and the original samples were restored from the cultures and returned to storage. "We should return within 1,000 years at the latest," the life science leader said, and the station leader entered this into their record system. "By then it will be obvious whether the seeds have taken hold, and if they haven't, we will have to determine why and whether to try again." The next world we visited had been seeded about 40 million years ago. "In this case, we are looking for signs of oxygen synthesis," the life science leader told us. "Our ground crews are sampling atmospheric oxygen, and also using spectroscopic samplers to look for mineral formations which might be acting as oxygen sinks. If we don't find signs of oxygenation, we will introduce cyanobacteria ourselves. If we do, we will look for the culprits to see if they are suitable for our purposes. If there's not much free oxygen, why not just go ahead and introduce your own cyanobacteria anyway? At every stage, our method is to give chance some time to work before we take action. The ancestors were clear that we should hope for evolution to surprise us before we impose our own order." Emma and I looked at one another. "I guess chance does happen sometimes," Emma said. "More often than it would suit some of us," the scientist said, and then he went on about his business. After a week and a half of sample collection, it was determined that there were oxygen-producing organisms at work, but they weren't nearly aggressive enough to transform the world's atmosphere in a reasonable time. Accordingly, our hosts set about another seeding operation, overseen by a different group of scientists. Apparently even the Curators have specialties. Our next destination was at this point about 60 million years ago. Our records indicate that suitable bacteria had evolved on their own and were on their way to exhausting the natural mineral oxygen sinks, so on our last visit we took no action. When we folded into the system, we found the world cloudless and brilliant white. "Iceball," I said. "Yes, a frequent result of oxygenation is that it oxidizes methane, a powerful greenhouse gas, into carbon dioxide, a less potent one, and the temperature drops. Life almost always survives this, but we have to wait for geological processes to introduce more carbon dioxide to get the temperature back up." "You couldn't fix this in a shorter time." "Not really. The environment isn't suitable for oxygen-using life to start making carbon dioxide, and even if it was, we really need more carbon on the surface, which we can get most easily by waiting for volcanoes to deliver it." Another notation was entered into the records, and we departed. It was a little strange after Earth's unpleasant recent history with too much carbon in its atmosphere to see how stark a problem too little could also be. The life scientists explained to us that at every level, from the single cell to an individual being such as ourselves, to the ecosystem of a world, life was a series of interlocking equilibria that had to be maintained. Maintaining those equilibria was what life did, and did excellently, but enough stress could cause those equilibria to collapse with dire consequences. After we left the iceball world, the leader didn't give us any hints as to what to expect next. When we came upon the next curated world after surveying its system from afar, it took our breath away. Along with the brown and gray of rock, it was also blue and green and the brilliant white of clouds. Let's survey it. As flyers descended to the surface, the leader explained, "This is a world which may be ready to pass on to the next crew. We want to establish that it has a stable ecosystem, maintaining an oxygen-rich atmosphere. The land will still mostly be barren, but there will be a lot of life in the water, especially the ocean shallows and freshwater inland lakes and seas. This is one of our most complex tasks, and we will be here for about a month determining the diversity and extent of that life. If we discover multicellular organisms or determine that the environment is appropriate to support them, we will pass this world along to the next development crew." They surveyed tens of thousands of samples, mostly using DNA techniques to sift for various gene sequences. Their computers were much more powerful than even human machines at analyzing this data to determine the mix and development level of the life forms that had contributed to a bulk sample. At the final summary meeting, the crew leader announced that all the elements were in place for the world to develop its own multicellular life forms, but that the breakthrough hadn't quite happened yet. In keeping with their policy of giving chance a chance, they decided to return in 50 million years to see if anything developed spontaneously before handing it over to be seeded with multicellular life. Our tour was over, and we folded directly back to Terlingua, where we found Quentin and the human form curator drinking scotch and playing pool in our underground lair. "A pool table? Really?" Emma said as Quentin took a shot, sinking his ball. "The barbecue joint is under new management, and they offered it to the first patron who could remove it for them," Quentin said as he lined up another shot. "And how did you haul it off? It's not like you have a pickup." Quentin looked at the curator, then Emma and I looked at him. "It's a bit large, but the range was only 2,300 meters, so well within the capability of my implant," he said. "You used the most advanced fold technology in the galaxy to boost a pool table. It did give us an advantage over the gentlemen who were planning to return with pickup trucks. And Quentin was kind enough to show me the game." "So you're a pool sharp too?" Emma asked Quentin. "Once upon a time," he said with a shrug. The scotch turned out to be Royal Salute, and the curator poured us shots. "So who's winning?" Emma asked. "Quentin is," the curator said. At that, Emma and I both raised our eyebrows. "You have a curator implant and Quentin is beating you at a simple match of physical skill?" "Yes, it is proving an interesting lesson well worth the diversion of the table. The simplest strategy is easily modeled, but is not a winning strategy. Quentin has proven able to use spin to make the ball travel curved paths, and to direct collisions which are far too chaotic to accurately model often enough to exploit them successfully. While I can control what the tip of the cue stick does far more repeatably and accurately than he can, my implant doesn't have a sufficiently accurate physical model of that aspect of the game to use that control." As if on cue, Quentin took a shot that sent the cue ball curving around one of the curator's balls that should have been in the way to knock another of his own into a side pocket. "Well, if his control is less accurate than yours, how is he smoking you at the game?" "I'm still trying to figure that out," the curator said. "I'm willing to take risks," Quentin said as he made another shot. "And I dispute his opinion of my control. I'm not analyzing the game as a physical system, but I spent a lot of years doing this and I still have the muscle memory. I may not know exactly what will happen when I let it fly. I notice Mr. C here always does. But it works often enough that I get a lot more opportunities than he does." "You're too conservative," I said to the curator. "Tending projects that take eons tends to make one a bit conservative," the curator admitted. "Yet it seemed like the opposite of that on our tour," Emma said. "At each step they understood that what they had done or were about to do might not work out. They said that about 10% of the final engineered collisions even failed to produce a suitable world." "Now that's a game of pool," Quentin said as he knocked in the 8-ball, winning the game. "There are parallels," the curator said pensively. "We have long established formulae for how much effort to put into each stage of the process. It is what you call a cost-benefit analysis, where we ask whether more effort and more time will increase the chances of success enough to justify that effort. At some point long ago, we determined that a 10% failure was acceptable for final engineered collisions, because halving that rate, while possible, might increase our commitment to each collision by a factor of 10. Planetary systems are so large and chaotic that the impossibility of precisely modeling everything is an obvious problem. It is rather surprising to see the same logic unfolding on the scale of the pool table. One of the lessons of our technological adolescence has been that logic unfolds almost everywhere, Emma said. It's why we were able to remake our world with satellite communications and reach its moon with impossibly primitive rocket technology, even though those rockets had a bad habit of exploding now and then. And our fold drive, I mentioned. They were only pretty sure it wouldn't fold the nearest planet into the sun. Which is why on our first test we made sure the nearest planet would be Mars instead of Earth. Losing Mars would have sucked, but the prize if we succeeded was interstellar travel. We took the shot, which you were only able to take because of your spectacularly primitive rockets, the curator said. And it didn't hurt that the civilians picked up the cue ball, Quentin added. But we didn't know that would happen, Emma said. We made the call that the small chance of losing Mars was worth the nearly certain opportunity of gaining the galaxy. It's a decision I participated in, and I would do it again today. We curators aren't so bold, the curator said. You have 2 more asteroid station tours arranged. One by the crew who guide worlds from multicellular life to what on your world you have called the Cambrian explosion, and another by the crew who gets those worlds ready for a critical path species to emerge. As we get closer to the critical path, you will see my people become less willing to diverge from practices which have been known to work in the past, because they have put more effort which they don't want to see wasted into getting to where they are. Won't we get to see how the critical path species are curated? You will, but that is done very differently. It doesn't require large crews or hardware, so our agents tend to just fold in with our implants carrying such small artifacts as we might need. Once in a while we need an amplifier belt. You'll meet those agents too, and you'll find they are very conservative. I would know because I am of course one of them. That thing about not wanting to lose your effort to date, in gambling we call that the sunk cost fallacy, Quentin said. It sounds like you aren't objectively evaluating the odds anymore. If you were, you would have either seen something like humans ages ago or we would never have emerged. You may be right, the curator said. As life becomes more complicated, it becomes ever harder to calculate the probable outcome of an action. It may be that we are doing what you do when you hit the cue ball, relying more on our memory of what has worked in the past than on a complete analysis of what is possible. This is worth some serious research on our part because if it is true, we have been falling short of our mandate to give chance a chance for a very long time. Are either of you novices at this game? The curator asked Emma and me. I am curious as to how your human tendencies would affect the outcome with neither of us having Quentin's muscle memory, and both of us having an implant. I'm no sharp, but too many weekends in the service there wasn't much else to do, Emma said. I've never picked up a cue, I said. Medical school doesn't provide a lot of time for recreation. Quentin gave me the same brief pointers he had given the curator. I didn't dominate the table the way Quentin could, but I won 6 out of 7 games as we killed the bottle of Royal Salute. The curation of early multicellular life turned out to lack drama. Although great changes were occurring as we visited more and more developed worlds, those changes were mostly visible only through the lens of a microscope or the output of a gene sequencer. All the worlds we visited had blue skies and seas with blue-green shallows and land masses that were mostly still sterile brown and gray. No dramatic interventions were contemplated, and none of the worlds was expected to fail. If life did not develop appropriately by a certain point in the host star's evolution, it would be kicked by seeding with viruses or entirely new organisms as appropriate. The evolution of the host star is what drives us, the team leader explained. It takes enormous amounts of time for the kind of changes we want to see to happen by chance. But as we wait, the star is also burning its nuclear fuel, becoming hotter and nearer to the nova that will make it a red giant. The habitable zone moves out as the star gets hotter, and generally a world that is near the outside of the habitable zone when we form its moon will be inside the zone and uninhabitable long before the nova. We try to make sure life becomes complex in time to enjoy some eons of that complexity before it is annihilated. It takes a succession of small miracles for organisms that start as loose confederations of single-celled organisms to develop the strategies that make it possible for them to create specialized organs, isolate the interior of their body from the environment, and to maintain that interior environment as they haul themselves out of the sea and colonize the continents. We watched 3 seeding operations, all of which proceeded similarly, although they involved very different biochemical agents and were run by different specialist groups. The last world we visited had large areas of green on its continents, but these turned out to be forests of giant fungi which were devoid of animal life, and the atmosphere was nearly 30% oxygen. Usually the oxygen load will spur development of animal life to make use of it, but for some reason that hasn't happened here. We will have to give it a kick or this ecosystem will burn itself out. If we can, we use viruses to give existing organisms extra capabilities which can be enhanced by natural selection. But in a case like this, we may have to resort to introducing entire families of library organisms to mitigate the developing crisis. Life manages to do amazing things on its own, but it also manages to paint itself into corners with depressing frequency. At some point, one of the scientists told us that their records showed that world CI 1742660, known to its inhabitants as Earth, had not developed its Cambrian explosion spontaneously. It had been seeded to give advanced life a chance to develop before the sun made it uninhabitable, a transition they expected in about 1 billion Earth years. With the aging cure, it was not out of the question that Emma and I could live to see that happen. When we returned to Earth, the giant fold ship Alexei Leonov had taken on its load of fold drive manuals, scientists and tourists, and had been replaced at the loading terminal by the Rocinante. That ship was scheduled to finish loading within 8 months, at which point the publishing operation would be shuttered, and the whole enterprise would consist of the 3 ships exploring the galaxy. Everything seemed to be going fine without us, so we folded over to the last Curator asteroid station we would visit. Unlike the others, this one was not unique. There were 3 similar stations doing the same duty of curating worlds from the earliest land-based life toward a species capable of taking the critical path. "We have about 12 million worlds in our index," this leader said. "When we first get them from the last crew you visited, we visit them once every few million years. As life becomes more complex, it also becomes likely to undergo more rapid change, and we find that if we visit less than every 250,000 or so of your years, we miss important transitions. Those fellows often have to seed worlds because they simply don't develop, but once life reaches this point, it does nothing but develop. Our biggest problem is when it develops into a dead end that won't lead to the critical path." This time there was no clean progression from simple to complex worlds. At this point you can't look at the life forms of an ecosystem and tell how long it's been developing, or how far along it is toward our goal for it, we were told. Forms ebb and flow in ways we still can't model predictably. We have had worlds transition to the critical path in as little as 30 million years after we took over their index, and some of those with no intervention at all on our part. We've had others that simply never developed, despite repeated interventions to correct dead ends, and which we eventually abandoned because their stars were becoming too old. "What exactly do you mean by a dead end?" Emma asked. "Your own world provides a perfect example. CI 1742660 developed a healthy ecosystem within a reasonable span after we got it, but then it spiraled into an arms race between ever larger predators and prey. We gave it nearly 100 million years, but it only ever got worse, and 65 million years ago we corrected the situation. That was obviously the right course of action because you fellows developed as a result. Except someone didn't think we were worth developing later," I said. "You have to talk to the critical path agents about that. I would say that your presence here today proves they were wrong. Considering that you guys seeded the galaxy with life, the idea that you could be that wrong about something is a little terrifying," Emma said. The leader made a tinny clicking noise which our implants identified as laughter. "The universe is inherently chaotic," he said. Then he looked thoughtful and said, "And I mean that in your technical sense, not your vernacular sense. The quality you call omniscience is simply impossible. There is no state of existence so advanced that one becomes incapable of misunderstanding a situation or making a mistake. We are proof of that, and we have only made a garden of one galaxy. We often wonder why the Curators never expanded beyond the Milky Way. Our estimates of the natural rate of development of advanced life suggest to us that this galaxy now contains more advanced life than the rest of the universe. Why would we need more?" It turned out that other than breaking up the logjams of dead-end evolution, this crew really didn't do much with the worlds under its watch except to turn them over to the critical path agents when something promising emerged. That doesn't happen very often, so we didn't get to see any examples, but we did get to see a world marked for a cleansing correction. Worlds where all the continental land masses are connected are a problem, especially when all those land masses are tropical in climate. I wanted to show you this world because it is very similar to yours when we intervened. There are both predator and prey animals massing over 100,000 kilograms. They are very highly specialized and unlikely to develop intelligence, and their presence makes life perilous for any other life form that might show the kind of promise that we want. One way or another they have to go. The monsters of this world strongly resembled dinosaurs, except that they had scales instead of feathers and beaks instead of jaws and teeth. Imagine a 40-foot-tall, 100,000-kilogram carnivorous parrot. The herbivores had appropriate defenses that made them impregnable to smaller predators, and even the trees were enormous to keep from being completely devoured by the giant herbivores. There were few niches where smaller animals could thrive, and none stable enough to allow for critical path development. We're not going to make the correction now because we have to monitor it for a while when we do. But within 1,000,000 years or so, we will return for one final survey, and barring a miracle, we will throw a rock at them. How would you do it? I asked. The leader activated a display. We pick a suitable rock, usually a moonlet of a gas giant since those are easiest to find. The limit for fold amplifier belts is about 20 kilometers diameter. We look for a suitable impact point on the target world. We want ocean shallows so that we can create a tsunami, as well as sulfate minerals if possible to create toxic rain. Equatorial so that both the north and south hemispheres will be affected equally. We wait until the rock's existing orbital motion is aiming it at the right angle, and fold it to within about 1,000 kilometers of the target, to give our delivering agent time to fold out before it strikes. One of our paleontologists once said that the Earth's KT impactor couldn't have landed in a worse possible place, I said. That wasn't by accident, was it? Of course not. Life is surprisingly resilient, and we need to be sure the reset is complete. Life at this stage always comes back, but we need it to come back without the giant monsters dominating the ecosystem. Later in our quarters, Emma was pensive. Within 1,000 kilometers, she said with a heavy sigh. It's not even sporting. It's an assassination. They're in the way, though, I said. And it's not our garden, really. Not everything is in the way, she said. To get rid of the monsters, they kill nearly everything. Nearly every individual of every species. Enough that a lot of the smaller species will have no surviving individuals either. Isn't that counterproductive? When we brought it up to the mission leader, he made a gesture our implants recognized as a shrug. We tend a lot of worlds, he said. We don't have time to be more surgical about it. We've been doing it this way for eons. Look, the world we just visited, you're pretty sure it's going to need a reset, aren't you? Unfortunately, yes. When we carry it out, we'll also probably spend several months watching the outcome, which distracts us from the rest of our mission. But it has to be done. And you don't really want to wipe out everything, right? If you could do it surgically, what would the thresholds be? Well, we're most concerned with both predator and prey animals that mass more than 10,000 kilograms. Intelligent species with primitive weapons can deal with animals of that scale, as your own ancestors did, but they can't deal with animals that mass 100,000 kilograms. Would you mind if we humans took a stab at this problem for you? I think we might have a way to do it that leaves the smaller animals and the overall ecosystem much more intact. That would be an interesting experiment. I would certainly see no reason not to let you proceed with such a plan, since we could always go ahead with our method if necessary. What exactly will you be doing? Let's keep in touch, Emma said. I have to talk to some of our human friends.